So let's do some chemistry with aldehydes and ketones and oxygen-containing nucleophiles. So the aldehyde or the ketone will be the electrophile, and the nucleophile will be some oxygen-containing species. And the electrons, the lone pairs of electrons on the oxygen, are going to do the attacking. So in a couple of our past lectures, we were talking about how electronegative nucleophiles typically form tetrahedral intermediates that are unstable, and as a result, the elimination of one equivalent of water occurs from the addition product. So the first example I want to give is if we were to use water as a nucleophile. And water is a poor nucleophile, and so therefore, just like when we were using nitrogen-containing nucleophiles, it's going to be in our best interest to do these reactions under acidic conditions. So we catalyze the reaction with an acid. In your body, these reactions typically are catalyzed by enzymes, biological catalysts. Let's just do just a generic water addition to some sort of, say, ketone. So I'll do just a generic addition of water to a ketone. So I'm going to draw the ketone. We can just let these be R groups. And I'm going to add some water to this. In fact, actually, I'll draw this out a little bit more suggestively. You could have just written H3O plus over the arrow, but we'll do it like this just to show. This will be catalytic and acid. And what you get is going to be a molecule where I have two hydroxyl groups coming off of the same carbon. This type of a molecule is called a hydrate. And a hydrate is a compound that has two hydroxyl groups on the same carbon. How does this work? So it's going to look pretty similar to the mechanisms that we've done for the nitrogen-containing nucleophiles. So I'm going to take my generic ketone here, just R, carbonyl, and then R. And I'm going to add a catalytic amount of acid. What I'm going to get, when I protonate this carbonyl, I'm activating the carbonyl and making that carbon more susceptible to nucleophilic attack. Because again, if we attack the carbon, we can dump the electrons up into the oxygen and quench the positive charge. So along comes our nucleophile. In this case, it's going to be water. Not the best nucleophile, but it's still nucleophilic all the same. We're going to attack the carbonyl, dump the electrons up into that oxygen, and we're going to get this tetrahedral intermediate. Another water molecule can come along, and we can deprotonate, dump the electrons onto that oxygen, and we get our product. Our hydrate down here. But, you know, if we can use the lone pairs of electrons on water to do a nucleophilic attack on that ketone, or if it was an aldehyde, you know, who's to say that we can't use an alcohol, right? That has a hydroxyl group, and that oxygen has lone pairs of electrons, and we can use that as a nucleophile. We get a different type of functionality, though, when we allow that to happen. Let me start with an aldehyde. In your book actually talks about these as if they're only happening to aldehydes. And there's like sort of two sentences where it talks about happening with ketones. And I just want to expand a little bit upon that because the name of the functionality that comes out of the reaction with a ketone is different. If you were to take an aldehyde and say react it with one equivalent of alcohol, so let me just take a generic aldehyde, and I'm going to react it under acidic conditions, so catalytic and acid, and one equivalent of some alcohol. We'll do R prime OH just to, have our R groups be different. They don't have to be different, but just, so we can keep track of stuff. What are we going to get? Well, we're going to get attack at the carbonyl, and we're going to end up with, instead of a hydrate, now we've got one hydroxyl group on here, and then we've got an alkoxyl group, right? So we have ether functionality and we have alcohol functionality, looks like, right? We have a name for this. This thing is called a hemiacetal. Hemi means half, right? So how did this happen? So a hemiacetal, we've got an alkoxyl group. So that's this right here, that green group. And we've got a hydroxyl group, highlighted in yellow, attached to the same carbon. How did this happen? So we're going to, I'll save time again and just protonate my carbonyl. In comes the nucleophile, so I'm going to draw this just a little backwards here. It doesn't matter. The electrons are going to come up and attack the carbonyl that's been activated, right? We're going to put electrons up onto that oxygen and quench the positive charge. What do I get? Tetrahedral intermediate. I'll draw the hydrogen just right now. Our conjugate base can come in. Because remember, this is catalytic and acid. We have to get the acid back again. I'm going to dump the electrons onto the oxygen. And we get our hemiacetal. I don't know if you guys can hear, my cat is snoring really loudly. So there's the hemiacetal. We've got our hydroxyl group and our alkoxyl group attached to the same carbon. What if I were to add two equivalents of alcohol instead of one? Well, if I added two equivalents to my aldehyde, so I'm going to take my generic aldehyde again, under acidic conditions, and now instead of one equivalent, I'll have two. What do I get? Well, you can imagine I'm going to add this group again, and I'll end up with two alkoxyl groups. So, two alkoxyl groups are going to be added to the same carbon with two equivalents of that alcohol. What's going to happen here? This is just going to be an extra proton shuffle, right? We're going to eliminate some water. Let me draw the mechanism down here. We'll have our generic aldehyde. So R carbonyl. I'm going to protonate this already just to save us some time. And I'm going to have one equivalent of the alcohol come in, so same as last time. We're going to attack the carbonyl. And we're going to form our tetrahedral intermediate. So our conjugate base is going to come in, and we're going to take this hydrogen away. Take it off of the oxygen. We're going to dump the electrons onto that oxygen, quench the positive charge, and we get this. This is our hemiacetal. If there's another equivalent of alcohol in there, I have my acid back again, don't I? So I can attack with these electrons, protonate that hydroxyl group. I end up with R, and then my alkoxyl group, and then I've got water, which is a pretty good leaving group, right? So what can I do? I can attack. Likely what ends up happening is the water is going to take off. And my alcohol is going to come in, my second equivalent of alcohol. And I'm going to attack right there. So what I'll get here, and this will be protonated, but that's okay because what do we have in the pot here? We have our conjugate base. So the conjugate base can come take this hydrogen, give the electrons back to the oxygen, and I get a full-on acetal. So we have two alkoxyl groups attached to the same carbon. I'm going to move this down to make it just a little easier to see. There you go. So right here we have our acetal. Now your book says that when ketones do this, they're called acetals. That's not true. I mean, I guess you could look at it that way, but the acetal is when you take an aldehyde and you react it with two equivalents of an alcohol. A hemi, or a half of an acetal, is where you react an aldehyde with one equivalent of an alcohol. I can do this reaction with a ketone, same two reactions. I get hemiketals and ketals instead. So what does this look like? The mechanism is the same, so I'm just going to draw the generic reaction. If I end up with just a ketone here, some generic ketone, and I am going to react this with one equivalent of an alcohol, so I'll just do R prime OH. And I catalyze this with some acid. What do I get? I get a hemiketal. See, we have half here. There's the alkoxyl group. There's the hydroxyl group. on the same carbon. What if I reacted this with two equivalents of alcohol? Generic ketone plus 2 ROH, R prime OH, so we can keep track. Catalytic and acid, and I get what? As you would expect, the full ketal. We've got some specific examples of these. Molecules that you are familiar with instead of generic R, right? Let's draw some specific examples. I'll give you an example of a molecule that has a hemiacetal. So glucose, for example, can exist in a few different ways. We can have the open chain, or it can cyclize on itself, and we can get alpha D-glucose or beta D-glucose. Let me draw beta D-glucose here. And I'll tell you what the beta means. It's not important for our specific chapter, but you might be curious. What's the difference? What's alpha? What's beta? So we have a couple of different ways to draw a carbohydrate. And I'll draw this with stereochemistry. We could either draw the Fischer projection, we could draw a Haworth projection, we can draw a chair conformation, or we can do this little ring thing that I'm doing. I prefer this. I'll tell you why. The Haworth looks very similar to this. It's sort of like viewing your ring from the edge on. But the reason I prefer this is because with the Haworth projection, all of these hydroxyl groups that are up or above the ring, they're sort of drawn like sticks, and sometimes they get stuck inside the ring and it's hard to see. So I think it's easier to see it this way. This is beta D-glucose. So beta D we know from our stereochemistry chapter, right? So if we put this in the Fischer projection, it'd be probably easier to see. The beta part of this just means that at the anomeric carbon, so here is your, by the way, hemiacetal. So, right, so we've got our alkoxy group. So this is, let that be just R on the other side of that oxygen. And then we have our hydroxyl group on the same carbon. So it's a hemiacetal. Glucose is an aldehyde. And so the beta part of this means that in the Haworth projection, for example, the hydroxyl group is actually going to be sticking up above the ring. If you were to draw this in the Fischer projection style, it would be on the left side of the Fischer projection. The alpha linkage would be on the right side, or it would be back or down in the Haworth projection. And a chair conformation, if you were to draw a chair conformation of this, this would be, for beta anyways, it would be in the equatorial position, and the alpha position would be axial. But that's an example of hemiacetal in a molecule that you are familiar with. What about, say, hemiketal? So I can draw an example of that. Fructose is a good example. If we're going to do carbohydrates, why not, right? This is not a bad idea, actually, because then I can draw an acetal and a ketal. I can just draw sucrose. So you just do a pile of sugars. So here we've got our hydroxyl group. So this is going to be beta D-fructose. So let me draw that a little bit better. We've got there you go. So this right here is our hemiketal. Fructose is a ketone, so when it's cracked open, that carbon right there is actually carbon number 2. Carbon number 1 is over here. So we've got what? We've got our hydroxyl group, And then we've got the alkoxyl group. And the rest of this ring can be the R. But I'm highlighting the oxygen with the beginning of that R group. So that's our hemiketal. And this is beta D fructose. You know, we can bond glucose and fructose together. So I can make, say, an alpha linkage off of glucose here. So let's draw like this. I can have, easier to just draw this with stereochemistry. Okay, and so this would end up being, gotta give myself some space here. That would be the alpha linkage where that was pointing down. Beta linkage on fructose. It's like almost like fructose is like holding a balloon up in the air, and the balloon is glucose. What else do we have here? We've got the rest of fructose here. And so, where's the acetal? The acetal is here. See? It's 2 alkoxy groups. Instead of a hydroxyl group. And then for fructose, the ketal is here. See how we've got the 2? So here I've got that bond for the acetal, and I've got this bond. For the ketal, I've got that bond and that bond. Let me highlight this. For carbohydrates, this is pretty specific. So we've actually created a glycosidic bond. The glycosidic bond this is not part of this chapter, but if you're taking a nutrition class, you might be curious about this. The glycosidic bonds are here and here. We've got an alpha linkage from the glucose and a beta linkage from the fructose. But we have in sucrose, we have an acetal and we have a ketal. Right? So that's a specific example of this functionality that we can create by reacting either 1 or 2 equivalents of an alcohol with either a ketone or an aldehyde. In the next piece of this chapter, I kind of want to go through and start talking about some different forms that our aldehydes and ketones can actually take. And then I want to talk a little bit about the acidity of the alpha hydrogen. So we have to zero in on the alpha carbon, look at the hydrogen that's hanging off of the alpha carbon, and talk about the partial positive charge that exists on that hydrogen because it's next to that carbonyl, an electron withdrawing group, right? That polar bond. We can do some chemistry by taking that alpha hydrogen off, and we can create a nucleophile out of our ketone or our aldehyde and use it to attack another aldehyde or a ketone. So your ketone can either be nucleophilic or it can be electrophilic, right? And there's a specific reaction I'd like to do with you guys to show you how that works. And that'll probably tie up chapter 9.